Okay, we want to talk about logarithms. And logarithms are kind of mysterious in some ways, but I think really have a fairly simple definition. Now, some of the applications and evaluating certain logs, you get some rules. It's not that bad, uh, but you got to get used to the rules. So let's just start. Here's a table for y equals 2 to the x. We got x there, we got 2 to the x here. Well, if x is 2, 2 to the x is 2 to the second, which you know is 4. When x is 1, you get 2 to the first, which is 2. When x is 0, you get 2 to the 0, which is 1. When x is negative 1, you get 2 to the negative 1, which is 1 over 2 to the 1, which is just 1/2. When x is negative 2, you get 2 to the negative 2. 2 to the negative 2 is 1 over 2 to the second power, 1 over 2 to the 2, and 2 to the 2 is 4, so it's 1 over 4. Now, bit over this. Hopefully you totally understand this. Now we want to make a table for log 2 of x versus x. What in the world is log 2? Well, the log 2 is the inverse function to 2 to the x function. Statement here, log 2 is the inverse to 2 to the x. That means if you calculate 2 to the x and then apply the log 2, you get x. Inverse functions. You put x into one function, put the value of that function into the inverse, then you get x. We learned that in the first chapter, and it's an idea that you really want to make sure you understand, because I've run into a lot of inverse functions. Once you have the idea, it's not a bad idea. Okay, it's not a particularly difficult idea, although depending on the application, it can be a little bit challenging. Okay, so it's inverse to 2 to the x. Well, long story short, to get a table for log 2 of x versus x, you just reverse the columns, switch x and y. So your y, which would be your 2 to the x here, becomes your x. 1/4, 1/2, 1, 2, 4. And your log 2 of x, that's your y in this table. That's going to be your x for the previous table. So you get -2, -1, 0, 1, 2. So we can now say log 2 of 1/4 is -2. Log 2 of 1/2 is -1. Log 2 of 4 is 2. The log 2 of a number is the power to which you would have to raise 2 in order to get that number. Statement is worth pondering. Okay. We could look at the graph. Notice that I give myself a little more room on the x-axis here. Okay, so I'm going to put x equals 2 here. I'm going to put x equals -2 here. Then I'm going to put y equals 2 here so that I can quickly sketch a graph of 2 to the x. And the lines I've drawn here are y equals 2, y equals 1. Sorry, y equals 4, y equals 2, y equals 1 here. Y equals 1/2 on this line, and y equals 1/4 on this line down here, pretty close to the x-axis. There's a graph of the log 2 function. A rough graph, but there it is. Now, if I want to graph I'm sorry, there's a graph of the exponential function. This is y equals 2 to the x. If I graph the log 2 function, then I've got to have a line for x equals 1/4. Well, here's x equals 2, here's x equals 1, here would be x equals 1/2, and here is x equals 1/4. Equals 1/4 on this line, x equals 1/2 on this line. Okay, when x is 1/4, y should be -2. Where's -2? Well, -2 is as far below the x-axis as 2 is above. So I'm going to say that this -2 line is maybe here. So that when x is 1/4, y equals -2, we draw the point at the intersection of those two lines, the x equals 1/4 and y equals -2 line. Then we have a point. Then when x is 1/2, y is -1. Well, I've drawn the x equals 1/2 line. And there's y equals -1, so here's a point. And then the x equals 1 line, well, right here it is, and y equals 0. Then the x equals 2 line intersects the y equals 1 line. Well, we have the y equals 1 line and the x equals 2 line, so we have a point here. And then we've got to have x equals 4, y equals 2. Where's x equals 4? Well, from here to here is 4 units, so we go from the origin 4 units. We get out to about here. Or we could say here's 2 and 2 more. Gives us x equals 4. Now we intersect the y equal 2 line with the x equals 4 line. And we get a curve. Now, if you happen to be vision impaired, can't see what I'm doing with this graph, we can go back to the table and you can make the table, which something we learned to do earlier in the course. And you can, one way or another, visualize or plot these points. Okay, you will see that the 2 to the x function has an asymptote at the negative x-axis. Now, when you switch x and y to get the log function, the asymptote of the log function will be at the negative y-axis, because if the asymptote, the horizontal asymptote of the 2 to the x function is at the negative y-axis, then when you switch x and y, you're going to have an asymptote at the negative x-axis. Now, if you can see that, that's great. If you can't see it, understand it, that as you, okay, for the 2 to the x function, as x goes from 2 to 1 to 0 to -1 to -1/2, the y values go from 4 to 2 to 1 to 1/2 to 1/4, each one being half of the previous. So if we continue this on to x equals -3, -4, -5, we're going to get 2 to the -3, 2 to the -4, 2 to the -5. And the 1/4 value that we get for x equals -2 cut in half gives us 1/8 when x equals -3. Cut that in half, we get 1/16 when x equals 4. Cut that in half, we get 1/32 when x equals 5. Okay, by the time x gets up to 10, we're going to have 1 over 1,024. And what's that do to the graph? On a graph, we have a horizontal x-axis, and the y values keep getting, every time we move over 1 unit to the left, the y values become half as great. So we move twice as close to the x-axis. If you keep moving twice as close to the x-axis, pretty soon you're going to be making very tiny moves, and you're going to be a very tiny distance from the x-axis, but you'll never get there. You can keep doing this till the end of time, and you will never reach the x-axis. You might reach the line you draw for the x-axis, because that line has some thickness, but you're never going to reach the x-axis. So that's what I mean by the horizontal asymptote for the 2 to the x function. Then similarly, when you do the log x function, the y equals log base 2 of x function, you're going to have a vertical asymptote at the negative x-axis. Now I can draw that. I got to keep going twice as close, and pretty soon my graph appears to merge with the x-axis, even though if I'm drawing geometric lines and points and curves, they have no thickness, and I can't draw anything with no thickness. And they never actually do merge. Okay, well, you want to understand that about asymptotes. The other thing we see is there's a symmetry to this graph. Now, I should have drawn this graph with equal scales on the y and the x-axis. I didn't. My y scale was compressed so that the y equals x line is probably going to look a little bit distorted. But you can see the description in your text, or you can imagine it. If we connect each point on the 2 to the x graph, each of the points we draw, -2, 1/4, -1, 1/2, etc., to the corresponding points in the log x. So we draw a line from x equals from the point -2, 1/4 on the 2 to the x graph to the point 1/4, -2 on the log base 2 of x graph. That line, if x and y have equal scales, will cross the y equals x line at a perpendicular. And no matter how you draw it, if you draw it accurately, that y equals x line is going to go halfway between the 2 points. That is, it's going to bisect the line segment from, say, the point -2, 1/4 to the point 1/4, -2, or from the point 1, 2 to the point 2, 1, etc. Okay, well, those are important geometric properties, help you visualize things. I'm going to stick with the log base 2 graph. There are two other graphs that are very important. The log base e graph, inverse to the e to the x function, and that's called the natural log. Well, actually, I better write that one down. I'm not going to do a table, but right, log base e of x is inverse function to e to the x. Log base e of x is what we call the natural log of x. So instead of writing log base e of x, we write ln for log natural of x. Okay? Now, in some computers or calculators or devices or whatever, the natural log is so natural that you call it the log log of x. But the log log of x, log of x means usually the inverse function to 10 to the x. And of course, the log base b of x is the inverse function to b to the x. So b could be any base. B stands for base. we can easily make tables for the e to the x function, for the natural or the natural log function. Well, for the e to the x function in reverse columns to get a table for the natural log function. It's not going to look too much different than the base 2 log because e is a number that's not all that far from 2. It's about 2.718281828, but it doesn't repeat. Okay, it's about 2.7. You could do log base 3 of x. Just write the 3 to the x table and reverse the columns and see where that log is. The 10 to the x function is a little impractical to graph, simply because 10 to the second power is 100, 10 to the negative second power is 1/100th, and to locate 1/100th in the same graph as 100, well, 1/100th is 1/10,000th of 100. Okay, so you have to have one point that's 10,000 times as far from the x-axis as the other. Okay, so it's kind of impractical to graph, although it's very handy for visualizing the way large numbers behave in base 10 system. So it's an important, the 10 to the x function and the log x function are very important in many scientific notations when you talk about very large quantities or very small quantities. The other log functions are very handy in solving a number of equations, solving the equations you get in a number of very important applications. Okay. Well, that's what a log function is. And there are some properties of log functions that are important, and you have to practice these properties so you remember them, so you can use them. One is that the log base b, and I'm just going to use base b, it could be base 2, base e, which would be natural log, could be base 10, log base 10, could be log to any base you want. I'll say log base b of a plus log base b of c equals log base b of a times c. Now, you might wonder why this is. I'm not going to detail the connection because it really should be detailed in this course, but I would leave that for the pre-calculus course. Okay, this is the reverse side of the rule of exponents. It says b to the a plus b, a plus c, sorry, equals b to the a multiplied by b to the c. You see that with a plus c, on one side we have the sum of a and c. On the other side, we have the product of b to the a and b to the c. So we have an expression with a sum in it that becomes a product. Here, the right-hand side is a log of a product. We started with a sum of two logs. Okay, so it shouldn't be surprising that something like this might happen. You want to treat, well, no, I'm not going to say anymore. This is the rule. It's related to this rule of exponents, which should be familiar to you. Okay. Another is log base b of a to the p, some power of a, equals p times the log of a. This is related to the fact that let's just use b to the a raised to the c power equals b to the a times c. Okay, the law of exponents, we do a power of a power, giving you product of the powers. Here we have a raised to the p, which is a power of a. Here we have a multiple of the log of a. Okay, there's an analogy between these, and there's a fairly short path to explain why this is the case. Again, I'm not going to get into that explanation in this course. There's another rule that I think and have always thought is unnecessary because these two rules imply the third rule, but it can be handy to know. It's a log base b of a over c pause a minute because there's a connection I want to make there. Okay. Something I probably should have said before I said this. You notice log base b of a times c is a log of a plus the log of c. Okay. If instead you do the log base b of a divided by c, it shouldn't be too surprising that what you get is a log base b of a minus the log base b of c. Now, that's a rule that really follows from these first two, but I'm not going to detail it. When I first saw logs at the tender age of, 15, it's pretty obvious to me that these two rules made this one unnecessary. I still think it's unnecessary, but since people like to use it, I'll bow to the conventional wisdom and we're going to include it. Okay, another rule is that the log of 1 is 0, always, for any base. Okay? And that's because b to the 0 equals 1. And this is a direct translation. So now you have the means of combining different, of simplifying various logarithmic expressions. For example, what's the log base 2 of x plus a plus the log base 2 of x plus b? Well, we have one base 2 log added to another base 2 log. The first rule I gave you, log base b of a plus log base b of c equals log base b of ac. And I'm going to kind of keep my variables or my symbols consistent. And then log base 2 of x plus a plus log base 2 of x plus c. Well, again, if you add two logs, what you get is the same thing as if you did the log of the product. So log base 2 of x plus a plus log base 2 of x plus c is a log base 2 of x plus a times x plus c. Okay. What's a log base 2 of x plus 5 squared? Plus log base 2 of x minus 2. Well, by the rule, first rule, Well, let's use the first rule. Log base 2. We get the log base 2 of x plus 5 squared times x minus 2. More commonly, we're going to see expressions like log base 2 of x minus 3 to the fourth times x plus 2 squared. That's going to be log base 2 by the first rule again, of x minus 3 to the fourth added to the base 2 log of x plus 2 squared. But log base 2 of x minus 3 to the fourth is an example of the expression in the second rule. Log base b of a to the p is p log a. So here we have x minus log base 2 of x minus 3 to the fourth by this rule. This equals 4 times log base 2 of x minus 3. And log base 2 of x plus 2 squared is 2 times the log base 2 of x plus 2. You'll see a number of applications, examples in your text, and you'll have a number of these to work out. They're not particularly difficult if you remember the rules. But of course, you want to be careful how you do the homework. You don't want to sit there with a list of rules in front of you for every problem. You might want to have that list in front of you for a few problems. You might want to practice on some other problems that aren't assigned with that list in front of you. But you need to work these until the list comes, well, until the list is embedded in your memory. And then you need to work some a couple of days later and bring that list out of your memory in order to solidify these rules in your memory and get the feel of the rules. Okay, well, that's up to you. There are other applications we can make, but in this course, I'm just trying to give you the bare bones, the really essential ideas, the essential principles, so that when you see it in your recalculus course, you'll be able to to apply it to more difficult problems. Okay, now, one of the most important applications of logarithms is in solving equations. So let's say we have the equation, well, exponential equations, okay? So I'm just going to write an equation here, which is b to the a equals c. This is an exponential expression. B is raised to the a power, set that equal to c. This is equivalent. I'm writing a equal sign with an arrow on each hand, meaning is equivalent to log base b of c equals a. So this is something you want to use so many times without having it in front of you, pulling it out of your memory every time. You want to use this a number of times so that it becomes a useful tool for you. Okay? Now let me show you how useful it is. let's just solve a simple equation. 3 to the t equals 2. Now, how do we solve this? T's up here in the numerator. There's nothing you can do to both sides. None of the things you do with linear equations or quadratic equations or any other kind of equation is going to allow you to operate on that t. You can't get that t out of the exponent except by using the rule I just gave you. Okay? If you try to divide by 3, well, if you divide 3 to the t by 3, you divide 3 to the t by 3 to the 1, which gives you 3 to the t minus 1. You still got a t up there in the exponent. You could try subtracting t from both sides, but the t in the exponent is not going to be affected by subtracting t from the 3 to the t expression. Well, what you do is, so this is a form b to the a equals c, with 3 taking the place of b, t taking the place of a, and 2 taking the place of c. So we can say that this 3 to the t equals 2 is the form b to the a equals c, as long as b equals 3, a equals t, and c equals 2. So I could say it is equivalent to log base b of c equals a, i.e., using the values we've identified for a, b, and c, log base 3 of 2 equals t. Now we got t here where we can operate on it. We don't even have to operate on it. We know what the value of t is. We just found it. T equals log base 3 of 2. Now I'll write that with the t on the left. And there's actually another rule that we use for logarithms. Log base 3 of 2 is the log of 2 divided by the log of 3. And you have an LOG button on your calculator. You know, in order to dumb people down, probably most calculators now have a log base b thing where you can put in the b and the number and it does it all for you. I prefer you do like log 2 over log 3 because there's an important property of graphs, a vertical stretch, that's involved with this kind of a rule. I'm not going to specify that right now, but I want to see log base 2 over log base 3. Okay, I mean log of 2 over log of 3. And this is any log. You could use a natural log, which you have on your calculator. Natural log of 2 over natural log of 3. I'll say etc. Doesn't matter what base this log is. The log you use for log of 2 over log of 3. In order to calculate log base 3 of 2, you're going to do log 2 over log 3, and those two logs could be any base. Could be natural logs, could be base 10 logs, could be base 2 logs. Okay, there it is. You can look that up. You can work that out on your calculator. There's a connection to the graph that I'm tempted to make, but I'm going to do a more complicated equation, then I might come back to that. In the application of the graph, or the application to the exponential function is 3 to the t equals 2 when t is a half-life of the 3 to the t function. Okay, we might come back and make that connection. But it's the idea of a half-life, or doubling time. Sorry, it's a doubling time, it's not the half-life. And when t is the half, I just said it again. When t is the doubling time of the 3 to the t function, 3 to t is going to equal 2. There's much more I can say. And maybe we'll in this course, and maybe I'll leave that to your calculus course. Okay. Let's take a little more complicated. 5 times 2 to the t minus 6 equals 4. Okay. Now, this is not of the form. I'm going to write over here, I'm going to write the two expressions. B to the A equals C is equivalent to B of C equals A. Okay. 5 times 2 to the t minus 6 is not of the form b to the a. And it's certainly not of the form that involves the log because there's no log in there. There's an exponent. There's a 2 raised to t minus 6. That would be a b to the a. But we have 5 multiplied by that. What are we going to do about that? Well, we can put the equation 5 times 2 to the t minus 6 equals 4 into the form b to the a equals c simply by dividing both sides by 5. So we can write 5 times 2 to the t minus 6 divided by 5 equals 4 divided by 5. And the 5s will divide out on the left-hand side, giving us 2 to the t minus 6 equals 4/5. Now we can apply the rule. I urge you to kind of write this out. Write out, this is the form b to the a equals c with b equal to a equal t minus 6, c equals 4/5. So log base b of c equals a. And again, write this out, because when you write it out without looking at a copy of it, when you write it out, you reinforce what you're in the process of learning, and you're more likely to remember it later and to be able to use it, to be able to think in terms of this conversion. And you'll understand the concept much better in a much shorter time. So you write this out, and I say that, and almost nobody ever does it. Okay. Those who do almost always make high grades in the course because they have that work habit. Okay. And they understand what it takes to learn something. Okay. Form b to the a equals c. Okay. That means that log base b of c equals a yields log base, what's b? 2. What's c? 4/5. That should equal a, which is t minus 6. Okay. At this point, sometimes, there's a tendency to get a little confused. Log base 2 of 4/5 looks like a complicated expression, but it's just a number that's very easy to evaluate if you have a calculator. You don't really have the means to evaluate it without a calculator. There are things called Taylor expansions that could be used, but that would be 3 pages of arithmetic to get a few decimal places. You wouldn't want to do that. And nobody wants to do that. Okay? So anyhow, you have this equation. Just think log base 2 of 4/5 is just some number equals t minus 6. Now, how are you going to solve for t? Well, you're going to add 6 to both places, both sides. Now I'm going to reverse sides. I'm going to write t minus 6 plus 6 equals log base 2 of 4/5 plus 6. So the t equals log base 2 of 4/5 plus 6. And that equals what? Well, now you have what you need to put in your calculator, and don't put in log base 2 4/5. Write out log of 4/5 divided by log of 2 plus 6. And then put that into your calculator. Okay. You're going to get something like 5.8, 6.8, 5.8, 6.8 or 6.9. And my brain's a little off due to a number of circumstances that will be less and less relevant day to day. Okay. So here we have it. Put that into your calculator. And I think you're going to end up with something like 5.8. I don't know. I might be right. I might be wrong. Normally I can visualize that a little better, but not today. Okay, so there we have it. It's a typical way of solving an exponential equation. You can also solve logarithmic equations. Okay, if I have log base 2 of x squared minus 9 equals 3, well, that's of the second form. The form log base b of c equals a, with b equals 2, a equals x squared minus 9, c equals 3. So it's equivalent to e to the a equals c, i.e. b is 2. Did I do that right? You know, I misidentified my A and my C because what I'm getting makes no sense. And I apologize. Like I say, things are a little off here. We got B right. We didn't get C right. C is x squared minus 9. And A is 3. I was a little careless when I wrote that down. Okay, so it becomes now 2. That's the value of B. A is 3. And where's my form? C is x squared minus 9. And I wrote that down without looking. Okay. Well, this means that x squared minus 9 equals 8. If we add 8 to both sides, we get x squared minus 1 equals 0, Or if we add 9 to both sides. No, if we do that, never mind. Probably ought to go back to bed here. Okay. Well, let's just solve this by adding 9 to both sides. We get x squared equals 17. So that x equals plus or minus the square root of 17. So we go from this equation, about which we have very little clue, to this equation, which is pretty easy to solve. Okay, so we can go from log form to exponential or from exponential to log form. A variety of problems that can arise here, types of problems, and you're going to see a good variety of them in your open math and in your pre-calculus course.